back from Thanksgiving holiday. I I want to believe you enjoy your Thanksgiving break, right? Okay, so before I get into business today, as usual, I'm actually gonna make some announcement because I know that some students don't normally check announcement section. So my first announcement today is that you can now all see that I've updated your midterm one score. I replace your midterm one score with the old score. I mean, sorry, with the new makeup score. Okay, so a situation where you score less than the midterm one, so I retain the old score. Don't know that was what I did, and situation where you score, maybe you score the same as midterm one, or you score more than midterm one, I added 2 points. So I know some of you we observe that. And I'm also going to do the same to midterm two. Now I want to tell you right now, midterm two makeup have already been uploaded. Okay, and of course the midterm two makeup will be on starting from Friday 12 a.m. in the morning up to Saturday 11:59 p.m. in the night. So you are all welcome to take the makeup. It's 30 questions, and I make those questions very easy. The moment you submit, you're actually going to receive your grade. Okay, so you are all encouraged to try the midterm to make up. So, like I said, it's already uploaded. So you're only going to have access to that on Friday, 12 a.m. in the morning, and it's going to be left open until Saturday, 11:59 p.m. in the night. So you only have 90 minutes. Oh, okay, so we're counting down into final. I provided makeup for midterm one. I provided makeup for midterm two. Of course, there's not going to be an opportunity for makeup in the final, and that's why I actually want you to try as to make sure you did well in the final. And of course, if you need clarification, make sure you reach out to me during my office hour. Okay, so let me tell you this. The final practice questions have already been uploaded. Get familiarized with the final practice questions. Okay, in the final practice questions, of course, the final exam for multiple choice will be cumulative. I'm going to say that again. The final exam, multiple choice, will be cumulative. But when it comes to short answer questions will not be cumulative. The short answer question will revolve around what you did in chapter 14, that we call more than two groups, chapter 11, then chapter 12, that we want to start, which is going to be the last chapter in the semester. Chapter 12 is going to be the last chapter in the semester. So 10, 11, 12, and 14. 10, 11, 12, and 14. Okay, the short answer question will revolve around that in the final. Short answer question will revolve around 10, 11, 10, 11, 12, and 14. 10, 11, 12, and 14. Why the multiple choice will be cumulative. Okay, I will advise that you get yourself familiar with the final exam practice question. Now, I want to start the last chapter of the semester that we call Analysis of Quantitative Variables. I also want to say my recordings for last, I think I've already uploaded all my recordings. Okay, I'm recording right now. I'm also going to record this. Okay, so what is new in chapter 11? We did analysis of categorical variables. Of course, I walk you through chi-square test. We use chi-square test to investigate. I also want to say my recordings for last, I think I've already uploaded all my recordings. Okay, I'm recording right now. I'm also going to record this. Okay, so what is new in chapter 11? We did analysis of categorical variables. Of course, I walk you through chi-square test. We use chi-square test to investigate if relationship exists between two categorical variables. And I remember we use relative risk to measure the strength of the relationship between two categorical variables. But you know what? Today, okay, in this chapter that I call chapter 12, analysis of quantitative variables. So if we want to study relationship between two quantitative variables, we can no longer use a chi-square test. Okay, I'm actually want to walk you through what we can use. Okay, so I present to you the analysis of quantitative variables in the outline. You're going to learn how actually do we figure out relationship between two between two quantitative variables. Then I'm going to walk you through. There are two techniques that we normally use when it comes to the analysis of quantitative variables. We use correlation, we use regression. I'm going to say that again. We use correlation, then we use regression. Okay. Now I'm going to tell you the difference between correlation and regression. And I need you to pay attention now. Okay. I need you to pay attention now. Okay. So when I talk about correlation, okay. So when I talk about correlation, okay, I'm talking about this guy now. So when I talk about correlation, so when I talk about correlation, I'm actually talking about relationship. I actually want to see, okay, there are there are two things I actually want to measure between two categorical variables. I actually want to look at number one, I want to look at the strengths of the relationship. Okay, I want to look at the strength of the relationship. Okay, and I want to look at the direction of the relationship. Okay, so when I'm talking about correlation analysis, okay, the correlation is actually measure the strength and the direction of the relationship between two variables. What do I mean by strength? Okay, it's going to be is it weak or moderate or strong? I'm going to say that again. By strength, I mean weak, moderate, or is it strong? That's what we mean by strength. By direction, we mean positive or negative or zero correlation. Okay, by direction, we want to see when we're focusing on the sign. Is it negative? Is it positive? Okay, so that's what we mean. Now, I'm going to give you an example now. Okay, if you take a look at this guy now. Okay, we collected this data about across so many variables, but we're only interested in the production cost and the performance of the book in terms of sales at our book office. Okay, so I want to see whether what is the relationship between the production cost and the sales. Okay, by that we want to see whether whether they move together or they move apart. Moving together means when one increases, the other one also increases, or when one decreases, the other one also decreases. That's what I mean by moving together. Okay, moving together means whatever that happens to one variable is also going to affect the other variable also going to move in the same direction. That's exactly what I mean. There's so many examples on that. Okay, a typical example in economics is the law of the supply. The law of supply said that the higher the price, the higher the quantity supplied. So the price and the quality supply, the quantity to be supplied by producer move in the same direction. Does that make sense? Okay, so that's what I mean by that. And at times, the relationship could be negative. Negative in the sense that when one increases, the other one decreases, which means they move apart. A typical example of that, you can look at the law of demand in economy. The law of demand, the higher the price, the lower the quantity demanded. I'm going to say that again. The higher the price, the lower the quantity demanded. Okay. Now, another typical example of a negative relationship could be the more you save, the less you spend. Okay. When you save more, you're going to spend less, which means saving and expenditure move in different direction. Does that make sense? So now, let me now tell you this. What is the difference between correlation and regression? I needed to pay attention. I've been talking about correlation. Okay, correlation and regression, they are two statistical techniques used in analyzing relationship between two quantitative variables. But let me tell you what correlation does. The correlation will enable us to see whether relationship exists or not. And when relationship exists, it's actually going to tell us the direction of the relationship, the direction in terms of is it positive or negative, and also going to tell us the strength, whether it is weak, moderate, or strong. That's what correlation is going to tell us. But let me tell you what correlation cannot tell us. Correlation cannot tell us when I using the relationship whether we can use if I have information about one variable, can I predict the other? Correlation can tell us that, but regression does. Okay, that is a different regression. If I know something about X, I can make a prediction about Y. If they have relationship, that's what regression, that is the difference. That is the job of regression. Okay. But correlation is not going to tell us prediction. Now, take a look at this guy now. Okay. If you take a look at this, we said, how well does the production cost of a movie predict how well it will do at the box office? For instance, you want to see whether the more you spend on the movie, you actually want to see whether the performance in terms of sales of the way the movie perform. Does that make sense? That's what you want to see. That's a prediction problem. Okay, that which means you are looking beyond relationship. Okay, you also want to look at a prediction. Okay, and when I talk about prediction, it is regression that actually do the job of prediction. Does that make sense? That's exactly what I mean. Now, what is the goal? The goal here is we actually want to explore a relationship between two quantitative variables. For example, why they call quantitative variable? The production cost in millions. Those are quantitative, right? And of course, the boss sales, or also is quantitative. Okay, so we want to look at the relationship between the two. Now, let me tell you this. If I want to look at the relationship between the two, okay, what are the approach? What are the approaches that we have? Okay, the one way is to look at is to plot the relationship, to plot the two variable graphically. I'm going to say that again. And that was what we did in chapter 3. You know, in my recording, where we actually met on Zoom, last Wednesday, prior to Thanksgiving, I actually I think I talked about chapter 3 as well. Or was it on Monday? We're talking about chapter 3, that has to do with if I have two variables that are quantitative in nature and I'm trying to understand relationship, what I can do is to plot them. You did that in high school where you plotted y against x. Okay, I'm actually, it's going to look like this. Okay, it's going to look like that. Okay, you're going to have a y-axis. You're going to, where s is going to be here and y is going to be here. Okay, of course, the data set that you have, okay, is actually going to look like this. Okay, where you have data set on x and you have data set on y. Okay, and you just graphically plot them. Okay, when you plot them, okay, you're actually gonna have something, okay, that may look like what I'm showing now. Okay, okay, where you can now say, okay, can I draw a straight line? Okay, it's not going to be all points that will be on the straight line. Okay, let me tell you this, the only condition under which all point is going to be on the straight line is when we are talking about perfect relationship. There is no perfect relationship anywhere in the world. No perfect relationship. Okay, so and that's why there's a graphical summary of of relationship between two quantitative variables. We normally call that a scatter plot. We call that a scatter plot. Okay, a scatter plot is a diagrammatical plotting of one quantitative variable, okay, against the other quantitative variable. And let me also tell you this, apart from having a diagrammatical plotting, we can also make use of a numerical summaries. Okay, so what I'm going to be showing you on Wednesday is how do we compute regression? How do we compute correlation using formula? Okay, and that is what we mean by if you take a look at approach number one, so you get to know the sample data using both graphical and numerical summaries. And let me tell you this, we always work with sample of data set, right? We want to believe relationship that we observe in the sample, okay, of the data set, okay, we're actually going to make a judgment about that. Okay, we're going to generalize that relationship on the entire data set. And that's what I mean by use the sample data to make inferences. Inferences means judgment. You want to take a judgment. Okay, inferences about the true population, true relationship. Okay, we're actually looking for true relationship. Okay, we're going to make use of data set, sample of data set, okay, to be able to figure that out. Okay, now I needed to take a look at this. I actually want to remind you of what we did in chapter 3. Chapter 3 is about having a graphical summaries. The graphical summaries, you having diagrammatical plotting of y against s. And let me tell you this, for, if you have two quantitative variables, you need to first identify which one is going to be your response, which one is going to be your explanatory variable. Okay, the one that's going to be your explanatory variable will occupy the horizontal position. We normally call that x, and the one we're going to the one we're going to call response variable will occupy a vertical, okay, axis in the graph. We're going to, that's going to be called response, and it's going to be denoted as y. Okay, that's what I mean here. I needed to pay attention now. Okay, okay, I said on the x axis, we're going to put the explanatory variable. On the vertical axis, we're going to put the response variable. Now, based on the question, based on the one we're dealing with now, don't forget, we want to look at the relationship between the production cost of a movie, okay, and the sales, okay, which one comes first? The one that comes first is you need to first make the movie, right? You need to first spend on the movie, right? The production cost is going to be explanatory variable. Does that make sense? The production cost will be the explanatory variable. Your response variable is actually going to be, the sales. Does that make sense? So the response variable is going to be in the y-axis, and the response variable will be in the y-axis, and the explanatory variable will be in the x. Now let me tell you this. If you have, after you've identified which variable is going to be response and which variable is going to be explanatory, and the moment you plot them, one of these things is going to show, and I need you to pay attention now. Oh my God, take a look at that. One of that is going to show in terms of shape. Okay, after having a diagrammatical plotting of x and y, one of this is going to show. And how do we make an interpretation of this? Okay, if you take a look at the first one, let me first prepare your mind. What we're trying to figure out here is a relationship. We want to know a lot of stuff. Okay, in the relationship, we actually want to know the strengths. That's number one. We want to know the direction. That's number two. And finally, can we have a way to make a prediction? If using the relationship if a relationship exists between two variables, if I have information about one, I make a prediction about the other one. But let me tell you what I just want to show you right now. What R represents, R denotes correlation. I'm going to say that again. R denotes correlation. Now we're working with a correlation right now. Okay, let me first tell you, let me tell you this, the possible values correlation can take a value between a negative 1 and 1. I'm going to say that again. Correlation takes value between negative 1 and 1. Okay, when R equal to negative 1, that's a perfect negative correlation. When R equal to positive 1, that's a perfect positive correlation. When R is very close to 1, okay, R is very close to 1, that's a strong positive correlation. When R is very close to negative 1, that's a strong negative correlation. Now, you see the way I'm interpreting correlation right now? If I want to interpret correlation, I'm actually going to mention the strength and direction whenever I want to interpret correlation, because correlation measures the strength and direction. Does that make sense? Direction and the strength. What do I mean by direction? Direction is you look at it, you look at whether it is positive or negative. Strength, you look at whether it is strong, weak, or moderate. That's what I mean by strength. Right now, because majority of the points are on the straight line. If you look at the first picture, the majority of the point are on the straight line. The majority of the point are on straight line, and you can see this is a positive in terms of slope. If you look at the direction, it's positive, and that is why you actually see that guy to be 0.945. You may not be able to know exactly, the values of R looking at the graph exactly. Okay, you're gonna know that when I give you a formula. We have a formula to compute R, but what I'm just displaying right now is the graphical, analysis of the relationship. Now take a look at the second one. That is in the negative direction, right? Okay, this is in negative direction. That one is in the positive direction. Okay, and if you take a look at this guy, that is slightly in the positive direction, but is kind of weak. Okay, any value that is less than 0.5 is weak. If it's less than 0.5, is weak. even though relationship exists, but that's a weak one. Okay, then I needed to take attention, take a look at the last one. When you take a look at the last one, that guy is more or less looking like a curve to me. But I said the exact correlation value, you'll be able to know that when I walk you through the formula. Okay, that when I walk you through the formula. So because of all of this picture, I'm actually saying this. Okay, when you look at the overall pattern, it could be linear. What we mean by linear, linear means a straight line. Linear means a straight line. Or it could be curved. But let me tell you this. Let me tell you this. When you have a curve relationship, we cannot use correlation. Correlation doesn't work for curved relationship. Correlation only work for linear, for straight. Does that make sense? Okay, when we have a curve, correlation is not appropriate for curved relationship. I just wanted to take note of that. Now, I mentioned something the other time. I mentioned something about what? I mentioned something about strength and direction. Very important. Okay, by strength, how closely do the point follow a pattern? Okay, it could be weak, it could be moderate, or strong. We don't normally mention perfect because there's no perfect relationship anywhere in the world. There's no perfect. Those are the extreme. And that's why we don't normally want to mention perfect. But we believe in theory. Perfect exists in theory. The perfects are the extreme, the negative one and the positive one. Okay, what we normally see in practice is something that is less than negative one, or that's going to be greater than negative one, but less than one. That's all. Now, for direction, direction is just talking about the positive, the negative, or even no direction, like zero. We could also have a zero correlation too. Does that make sense? Okay, now I want to explain what we mean by positive relationship right now. Okay, I said two quantitative variables are positively associated when high values of one of the variables tend to occur with the high values of the other. In other words, they move in the same direction. That's what it means. They go together. When this variable increases, the other one also going to increase. When this variable decreases, the other one also going to decreases. They move the same way. That's what it means. And that is there's a lot of examples you can cite here. Maybe you want to look at the relationship between the amount spent advertising and the volume of sales. I'm going to say that again. The amount spent advertising and the volume of sales. They move together. Or you want to look at the relationship between the amount of time you spend on social media. Okay, you want to look at the relationship between that and performance. When you spend a lot of time on social media, it will affect academic performance because you also need time to study. So they move together. So whenever two variables move together, they are positively related or positively associated. Now, when you talk about negative association, on the other hand, okay, yeah, I said, two qualitative variables are negatively associated or related when high values of one of the variables tend to occur with the low of the other, or vice versa, which means when one go up, the other one go down. We got a lot of example on that. The example on that is number one example is I think it's the example I use on the social media. When you spend so many time on social media, the exam performance could go down. More time on social media, exam performance go down. Okay. Now, in case of a positive association, when you spend more time studying, there's possibility your exam score is going to go up. That's a positive relationship. So for negative, you spend more time on social media. Okay. Of course, the exam score is going to go down. That's a negative. Or another example is the more you save, the less you spend. Okay. When you save more, then you're actually going to have low expenditure. And when you spend less, you save more. Okay. There's so many examples of that. Now, outliers also affect relationship between two quantitative variables. I told you the other time, outliers, according to Benkamp in 1982, is a data point that is not consistent with the rest. And it has to be managed. It has to be well handled because it's actually going to affect results. Okay? And that's why I said, are there any unusual points that fall outside the cloud of the data point? There's possibility we could have that. Now, I want to go into an example right now. And of course, so I'm gonna walk you through how analyzing quantitative variables is actually going to play out. Let's take a look at example 12.2. Is there an association between Olympic winning times for the 200-meter dash and the year in which the Olympic took place? The following is a partial data set of the Olympic winning times in seconds, starting in 1908 and ending in 1996. Can somebody remind me of the city and the country where Olympic was conducted in was hosted in 1996? Can somebody remind me for extra credit? Go ahead. Atlanta in the United States. Good job. Send me a message for extra credit. You know what you want to say? Oh, you wanted to say Atlanta too, right? Let me see. Oh, I can see. I can read your mind. So send me a message for extra credit. Okay. Now, Olympic, it was actually hosted by United States, particularly the city of Atlanta in 1996. And another Olympic is going to be hosted. The next Olympic is going to be hosted where? LA, Los Angeles, where? In our United States. Exactly. Yes, our current. Send me a message for extra credit. Okay, you know what I want to do now? We want to look at the relationship between the year, okay, uh, which is actually going to be the numbers of years after 1900. The first Olympic after 1900 was the one in 1908. Okay, 1908. Now, when you take a look at the year here, the variable here, 8 means 1908. Does that make sense? 12 means 1912 because Olympic is being hosted every 4 years. Does that make sense? And the time for 200-meter dash is what you're saying. You know what we want to, do you know what we want to investigate right now? We want to see the relationship between the time for 200-meter dash and the year Olympic was held. We really want to see whether as year is increasing, we want to see whether the time is increasing or the time is decreasing. That's exactly what we want to see. Do you all understand our intention? Okay. And of course, you know what is going to be the joy of the Olympic. The joys of Olympic is that when year is increasing, the one situation where athletes will break their record, breaking their record, minimizing, reducing the time. Does that make sense? Okay. Now, in this situation now, I told you, before you can go by way of graphical plotting, whether you want to go by way of graphical plotting or you want to go by way of a numerical analysis of the relationship, you need to first identify what is the response variable and what is the explanatory variable. I'm seeing a lot of final exam question here. Of course, they're actually going to ask you, You got two quantitative variables. Okay, what is the response and what is the explanatory variable? Of course, the explanatory variable will be the year, because before athletes will run a race, then Olympic need to be held. Does that make sense? And that is why the explanatory variable will be the year. Okay, then the response variable is going to be the time. Okay, the time for 200-meter dash. Okay, now how now for first we want to study the relationship right now, and we want to generate a plot. We want to go by way of a graphical summary of the relationship, generating a plot, and what is going to be the code in R. Okay, now I'm going to show you the code in R. Okay, the code in R is actually this guy. Take a look at that. You're actually going to write plot. After plot, the very first thing that will appear is your explanatory variable. My explanatory variable here is year. Explanatory variable first, followed by response. Response is time. Then after that, I'm actually going to, I want to label my X. I want to label my Y. Now, the X label, you can see represent the numbers of years past 1900. And of course, the Y lab is going to be the dash time. Okay, and what you can see, the PCS, maybe you're focusing on with the way the size of the graph is going to be. Now, this is the graph using the data set. I need you to pay attention now to this. Pay attention to this, okay? I'm saying something. I need you to look at. If you want to know whether it is a negative or positive, you can face your graph like this. Look at the way I'm facing my graph. Okay, do you see my left hand? You see that one? Okay, if it is positive, it's gonna come. Okay, now if you take a look at what I'm seeing now, okay, if you take a look at what I'm seeing now, this is a negative relationship. And what does negative relationship means? I told you the other time, okay? I told you the other time. Oh, give me, okay. Now, I told you the other time that, a negative relationship, based on what I'm seeing now, I'm able to arrive at this. Look at that. Okay. I mentioned strong. Why do I mention strong? Because most of these points are not far from the straight line. They are not far from the line of best fit. Okay, when the majority of the point are very close to the straight line, that indicates strong. When they are far from the straight line, that indicates weak. Does that make sense? If you take a look at this now, I mentioned strong, negative, linear, relationship. Okay, now the next thing is to interpret that in the context of what we are trying to investigate. Okay, so what I mean, 200-meter dash times have been improving. Okay, improving in the sense that, the good news athletes want to actually talk about is reducing their time. My daughter in high school, and that's also doing a PSEO. He's into athletic. I remember, I think was it in August, we were in North Dakota, because she do athletics, she 200 meters, 200, I think 4x1, long jump. So we used to travel. We travel at times, maybe I think in June, we're going to be going to Texas. So because of that, I'm able to, whenever she actually break her record, she's going to be happy. So which means what they want to do is to, improvement here means decreasing the time. That is improvement to them, decreasing the time. So what this guy is trying to say, as the time is increasing, as the year is increasing, okay, what happened to the time? The 200-meter dash is decreasing. So which means they move apart. Does that make sense? That's exactly what I mean. Any question on that? Any question on this? Go ahead. Okay, like whether something that we need to make the argument valid. Like which argument? Okay, that's it. That's a very good question. Um, to make the argument valid, we need a numerical computation, which I'm actually going to show you. So looking at the graph, the only thing I may not be able to tell looking at the graph what exactly the values of R correlation is. But I'm only going to say on average, I'm saying something negative and something strong. I may not be able to tell the particular value of the strong. So the only way to tell the particular value of the strong is when we go into numerical computation. That's a good question. Very good question. Okay, now you now know what we're gonna do. If I want to answer a question right now, if I want to know, the value, then I need a formula. Take a look at this. Oh my God, we are back at numerical, and that's what I call 3.22 numerical summary for measuring the strength of linear relationship for observational data. Okay, and which means we're now going to put, I need you to pay attention now. We need a formula. We want to have an exact value for correlation. And the only way we can get that is actually to, to have a formula so that we are going to, using the same data, if we compute correlation from anywhere in the world, we're going to have a unified result. Okay, now let's get started. But it's very easy. If you want to know the formula, you actually need to know some kind of components in the formula. And you know what? We've done them before. We just need to play around them and combine them and get our correlation. Now, let me tell you this. Take a look at this. I'm working with the X and Y data, right? X and Y, okay? I'm going to take a sample, but let me tell you this. If I take a sample size of N, okay, from X, I also need to take a sample size of N from Y. It has to be pairwise. Like this is, and that is what I mean here. Please pay attention now. It's very, very easy. I want everybody to score like 100% in the final. It's very easy. Okay. Okay. Now take a look at this. You know what this guy is saying? X1 to Xn. I got sample sizes this on X, and I get the same number of sample sizes on Y. Take a look at that. If I'm taking 10 observation in X, I also have to take 10 observation in Y. And there has to be pairwise. Okay. Now let me tell you, in X, oh my God, you already know how to find the mean and the standard deviation in this class. You find the mean of X, you find the standard deviation of X. Not only that, you find the mean of Y, you also find the standard deviation of Y. How many things do you need to find? 4. Okay, 4. Now, those 4 now, we now want to use them now. You're going to see now. Oh my God. Look at this. That is the formula for correlation. Take a look at that. That is the formula for correlation. You know what I'm doing right now? I'm now going to use the idea of a z-score. Do you remember z-score that we've done before? Now I needed to pay attention. Okay. Take a look at this guy. Oh my God. This guy is a z-score for X. For X. Z-score for X. This guy, z-score for Y. Do you understand that? And that is going to be super easy because I already know the mean of X. I know the standard deviation of X. I know the mean of Y. I know the standard deviation of Y. All I'm going to do here, I'm actually going to have several z-scores. Don't forget my X, they're going to be so many, right? Now, what I'm going to do, I'm going to multiply this by this. I'm actually going to sum them. When I sum them, one moment. Okay, so I'm actually check is using, give me 1 second. Okay, now can you see that now? And with that, you're actually gonna get your R. And that is the only way to know, the exact value that we're talking about. And let me tell you this, when you get your R, okay, we got properties of R, okay? The values of R does not change if we reverse the role of X and Y. Let's say, for instance, where you have X, you put Y, and where you have Y, you put X, R is still going to remain the same. So which means, take a look at this. When you are doing correlation, whether you switch Y for X or X for Y, it's still going to be the same correlation value. But when you are working with regression, it's not going to be. So, right now, we're working with correlation, right? Okay. Now, the values of R does not change if we change the unit of the variable. Let me tell you this. Let's say, for instance, we were in gram. We now convert to kilogram. Okay? The values of R is still going to remain the same, provided you convert the two variables to the same unit. When they were in the old unit and you make a conversion to the new unit, the values of R will not change. For instance, they spend naira in my original country, Nigeria. Has anybody heard about Nigeria before? Nigeria. Okay. Now let's say something is in naira. I want to convert it to dollar. If I compute correlation, the value is not going to change. Okay. I need you to pay attention to number 3. R only measure the strength and direction of a linear. I told you, straight line. The moment it is a curve, then we don't talk about correlation. Does not address relationship when we're talking about curve. Does that make sense? Only applicable to linear. Then I say arrow is not resistant to outliers. Okay. Do you know the reason why arrow is not resistant to outlier? Don't forget, mean is not resistant to outlier. Standard deviation is not resistant. And don't forget, in R, in correlation, we're using means and standard deviation. So if mean and standard deviation are not resistant to outlier, then correlation is not going to be resistant to outlier. Does that make sense? And that's why I say it is obvious, because the formula involved the means, okay, are not, okay, resistance to outlier. Therefore, the correlation will not be resistant to outlier. Okay, now this is, I told you the other time, the range of correlation. Arrow, we use arrow to denote correlation. It's going to go from -1 to 1. When arrow is greater than 0, positive. When it is less than 0, negative. When it's equal to 0, uncorrelated. Uncorrelated means no linear relationship. Okay, if you want to look at it in direction. If you want to look at it in terms of strength, if correlation is very close to 0, it is considered weak. Okay, if it is plus or minus 1, strong linear, it is arrow. If arrow equal to 1 or -1, we actually call that perfect. Okay, now I think I have some examples of that here. Take a look at that. Okay, what are the examples of that? And you know what? How do we do this in R? If I don't want to use the formula, oh my God, if the formula is taking forever, because the formula will require that you find the mean of S, the mean of Y, the standard deviation of S, the standard deviation of Y. If I have my data set, how am I going to find correlation in R? Oh, the other time, when let's say we already imported our data set into R, and data set is year and time. Take a look at this. Do you see that? I'm just going to write COR means correlation, COR. I'm going to write my explanatory variable first, followed by time. That give me that. Or if I even decide to switch it, I told you the other time, whether I switch S for Y or Y for S, it's still going to give me the same. Look at that. Okay? Whether correlation between year and time or time and year is still going to be the same. Now, based on that, now how do we interpret that? I said, therefore, there's a strong negative linear association. You see the way we normally say it. You mentioned the strength, the direction, and the linear relationship. Look at that. Between time and year. And what we got here, agree with the scatter plot. There's always going to be an agreement between the numerical result and the graphical result. Do you know what we've done today? What we've done today is to look at the relationship. We've not talked about prediction. Oh my God. If you want to talk about prediction, what we're going to do next is if I, based on the relationship that I got on the two variables, if I know S, can I make a prediction of Y? Okay, then that we call for the use of regression. This is where I'm going to stop today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.